Welcome to another unit of this Excel course. In this unit I'm going to talk about the normal distribution. So more or less the most common, most well-known distribution in all of statistics. And I want to show you in this unit how you can use Excel, first off, to get probabilities in relation to a normal distributed variable, and on the other hand, to find the so-called Z values, which we might need if we work with confidence intervals, if you are going to perform some kind of test on something, with a lot of different applications. And let's start with the first thing, with calculating probabilities. So assume we, for example, talking about having a bottle of water, which usually contains 1.5 liters. So we have our mean of 1.5. And then, usually if you have this filled via machine, this fluctuates a little. So if we have fluctuations can always be described via the standard deviation. Imagine here I have a standard deviation of, say, 0.02 liters. My question now would be, for example, what is the probability? So what is the probability that a bottle of water contains actually less than 1.45 liters? So something like this. This could easily be answered via the normal distribution. This can also easily be answered via Excel. Of course, here we're going to use like norm, that's the normal distribution, then dist. And you see here, he wants to have 3 values from me. The x value, that's actually here, the value for which I'm checking, so the 1.25. He wants to have the mean, the 1.5, and the standard deviation of 0.02. That's the values he wants to have, and then he finally wants to know, am I using the probability function or density function? Am I using the cumulative distribution function? With continuous function, usually using the density function doesn't really make so much sense. In particular, I couldn't really interpret the result from the density function, and I cannot interpret this as with discrete functions as being equal to, because the probability of a random variable being equal to something is for continuous variables always 0. So here, with a continuous distribution, like the normal distribution, only the value true, only the cumulative distribution function makes any sense at all. So we're going to use this here. Here this shows us the probability of this event occurring is actually 0.621%. And what about if I'm actually changing this to larger or equal to 1.45? In this case, I have to use the counter probability and turn this around to being 1 minus 1.45. The advantage here with continuous distributions is that if I take this counter probability, I would have usually with discrete ones a problem here because this is really smaller than. As I said just a minute ago, with continuous distributions, the equality case results in a probability of 0. So I could just add this here, and I would just add 0 to my result, which actually means I wouldn't change this at all. So here I can directly do it like this, meaning I can calculate the probability simply as 1 minus normal distribution, then x again as 1.25. The important part here, the normal distribution requires this lesser or equal to. So I always have to reformulate this so that it reads lesser or equal to, which I just did. Mean was 1.5, standard deviation was 0.02, and as I said, I'm using the cumulative distribution function. So here I get, well, does not surprise a lot because it's just 1 minus this value up here, 99.4%. Okay, so far so good. So this actually tells me how I can work with the normal distribution. Someone might be wondering, well, here I just used the normal distribution, but when I go here, I directly see two more. I see NORM.S distribution and those other stuff with the INV. So first off, the NORM.S distribution, I can just write this down. That's on the standard normal distribution. So this is the distribution where I already have a mean of 0 and a standard deviation of 1. So that's if I already use standardized values. Well, in this context, if I want to be more flexible, the normal distribution in the normal way is here, NORM.DIST, makes a bit more sense because then I don't have to standardize the values beforehand. Still, I could do this. So this is basically the alternative to this. So if I don't want to use any normal distribution, but the standard normal distribution, I just put a .s after the norm. Okay, so this tells me how I can calculate probabilities of normal distributed variables. If I want to go the other way around, I need to get a certain percentile of the normal distribution. In other words, if I'm looking for specific z values, I'm doing the whole thing the other way around. Now I'm setting the probability and I want to know what the corresponding value here is. So in other words, I'm doing the inverse of the normal distribution. So if I want to know what the value is, that more or less limits 5%. So the value where only 5% are smaller than, where 5% of the bottles contain less than. This value I can get with norm, then dot, and that's the INV, the inverse. Here again I need to have first the probability, that were the 5% I mentioned earlier. Then I need to have the mean, this was 1.5, and again the standard deviation of 0.02. So this tells me here 5% of my sample, 5% of all the bottles will have filling quantity of less than 1.46710 liters. So here, in this case, I set this value, I calculate the probability. If I work with the inverse normal distribution, I'm setting the probability and finding the corresponding value here. And well, I could also use this to get, as I said, my z values. My z values, however, refer to the standard normal distribution. So I put an s here and then take the inverse. For example, if I'm looking for the z value for 95%, I get the value which some of you might know of 1.6448. If I'm looking for the corresponding value for 2.5% or an error of 2.5%, this usually translates with two-sided tests into 0.975. That's the value which we usually know as 1.96. Well, here it's a bit more, with a longer decimal. And I see, if I round this up to the 4th decimal, I will get 1.96. Afterwards might become a bit smaller. But we recall this as 1.96, so that's well enough. So that's the values, or the possibility how I get the corresponding Z values. But I can also use this in this context and say, in this case, I can find out what actually the critical value here is. If I want to know the smallest 5%, if I go here with let's make this 10%, this would mean 10% of all the bottles will contain less than 1.474 something liters. And that's basically all the stuff I wanted to talk about in this session with regard to the normal distribution. So first off, we found out how we can use Excel to find probabilities with regard to normal distributed events. If I have the mean and the standard deviation, or if I put an .s after the norm for already standardized values. I also then discussed how I can find these critical values under assumption that I know the probability. So I'm basically doing the opposite from what I did before. That's why I'm using the inverse normal distribution. And if I use this with the standard normal distribution, I can get our Z values. That's also how we construct these tables for the Z values. Yeah, that's all there is I wanted to introduce in this unit. So I hope you enjoyed listening to it and you find additional material on Excel in the corresponding course, or if you take a look in the playlist on this course. So I hope to see you soon, and I say goodbye until next time.